Thank you. So, okay, I will start with some geographical notes. So Patrice started his, so he was born to mathematics in 83. He started his PhD thesis in the center of Paris with Michel Herman. And then just after 1 year, he got a position in Orsay before defending his PhD thesis. And he stayed there until he got a position of professor so Orsay in south of Paris, if you don't know, and then he went to Villetaneuse, north of Paris. And then 10 years ago, he moved back to the center of Paris. And so, okay, Parisian university are very complicated. So now, this year, he doesn't move, but the university name moves. So. Okay, so I will talk to, of course, not all his mathematics. I've picked some results I like the most. And okay, so Birkhoff attractor, local dynamics, generating functions, linkings, equivariant foliated Boer theorem, of course, and Hamiltonian dynamics. So, okay, the first work of Patrice was about Birkhoff's attractors. So I've put some example if you want something concrete. But so he considered twist maps of the annulus. So twist map. So on the open annulus, infinite annulus, you have the vertical lines, and you say that a diffeomorphism is a twist map if the image of every vertical line is transverse to all the vertical lines. Okay, so it's either twist on the right or on the left. And so dissipative means that the area is contracted, and also you assume that there is some bounded annulus which is inside itself. Okay, that's the hypothesis. And then you can define the Birkhoff attractor. So you have this annulus which is contracted, so you iterate, and you take the intersection of all the forward iterates, and that's almost the Birkhoff attractor. You have to remove some errors, that's some technical issue, so that you take some minimal separating continua in this. And so Birkhoff has studied this, so as you all know now, you have this invariant continuum, you can use prime ends from above and prime ends from below. So you get two rotation numbers, rho plus and rho minus. They can be equal if the attractor is a circle, for example, they will be equal, but they can be different. And okay, and so the result of Birkhoff is that if they are different, then you consider any number which is between those two numbers, and if it's rational, you get periodic orbit. So that was proved by Birkhoff. And Patrice, no? This result? Oh, yes. That? No, okay, that was, oh, sorry. So what was in Birkhoff's work?
Birkhoff proved that there exists a rotation, set of rotation number rho minus and rho plus.
Okay, just for, okay, rho minus and rho plus. Just
the boundary of the Birkhoff attractor, exactly on accessible point.
Okay. Okay. So, okay, Patrice reproved some result of Birkhoff, but this one, okay, he was new. Sorry about that. And also, if you take a rational number, you get periodic orbits, and if you take irrational number, you get quasi-periodic orbits. That's called Aubry-Mazur sets. And so Aubry-Mazur set is, well, it's a counter set invariant on which the dynamics is conjugate to the dynamics of a Danjois example on the minimal set of the Danjois example. Okay, so it's like a Danjois example, except in this setting you get it even when in examples when the map is smooth for Donjo example, you have to take only C1 DFO, but here you can get them in that setting. So in that work, Patrice was using topological methods, and Aubry-Mazur sets had been studied just before, but with variational methods. Okay, so let me go to local dynamics. So we start with a question which is not at all local. So this is an old question. It's an important question to decide on which space you can have minimal homeomorphisms. Minimal means every orbit is dense. So I don't know where this question comes, knowing if you can have a minimal homeomorphism on the sphere minus a finite set. Probably, so Besikovic in 51, he constructed a homeomorph of the open annulus, so the set minus 2 points, which is transitive. It has a dense orbit. And I think at first he thought it was minimal, but then he corrected himself. And so the question is natural after Besikovic work, at least. And so Patrice started working on this with Jean-Christophe Yocos in 88, I think. And they solved the annulus case, and actually all the cases, but the annulus case was the only one that was remaining. So let me review the different cases. So if you take an empty set, so you are on the sphere, and so of course a minimal homomorphism has no periodic orbit, but on the sphere, if you look, maybe F does not preserve the orientation, but you do F square, it preserves the orientation, so it's isotopic to the identity. So by Lefschetz's formula, it has to have at least one fixed point. So F has at least one per 2 orbit or a fixed point. So on the sphere, there is no minimal homeomorphism. That's easy. If you take X to have 1 point, then you are on the plane, and on the plane, if you have no other fixed point, if you have a minimal homeomorphism, it would have no other fixed point, so it would be a Brouwer homeomorphism, and Brouwer tells you that all the orbits are closed, they go to infinity, so it cannot be dense. So again, no minimal homeo. And then in 92, Michael Hendel proved that there is no minimal homeomorphism on the sphere minus a finite set of at least 3 points. So the remaining setting was the infinite annulus, the sphere minus 2 points. And they solved this with Jean-Christophe Yocos, and the paper appeared in 97. And okay, I would like to explain the easy part of the proof, the strategy. It's a difficult result, but there is some easy, nice part of the proof. So you want to prove there is no minimal homeomorphism on the sphere minus 2 points. So it's a proof by contradiction. You assume you have a minimal homeomorphism, and you want to see what will happen. So first, as I said, so it's a homeo of the sphere minus 2 point. So it extends to the 2 point north and south, maybe exchanging them, but after taking the second iterate, you can assume they are fixed. And let's assume for simplicity they are fixed. So you have a homeo of the sphere, which has 2 fixed points, and it's minimal on the remaining of the sphere. So in particular, no other periodic orbits, okay? So what you are going to do is study the local dynamics at the fixed points, north and south. So using the minimality hypothesis, you get lots of information on these fixed points. So for example, n cannot be a thing, certainly. There is no curve like this, because if you have a curve like this, then any orbit can meet this annulus at most once. Okay, so it cannot be dense. So there is no, so it's not a sink, nor a source. And also you have no small, well, you have no, small is not important here, but you have no compact, connected, invariant sets which are not reduced to the north point. So you cannot have hedgehogs or I don't know what just because you are minimal. Every orbit is dense. So these are strong hypotheses on the local dynamics at north, and so they call this kind of point saddle-like. And they prove that if the point is saddle-like, then you can, so of course, you can compute the Lefschetz index of the iterates. This is well defined because you have no other periodic orbit. So n is an isolated fixed point of f and an isolated fixed point of all the iterates. So the Lefschetz index makes sense. And they prove that the sequence of Lefschetz index is like this. It's periodic, and it takes almost always a value 1, but periodically it takes a value which is non-positive. Okay, so the example that you have to have in mind is the easiest example, of course, is a hyperbolic saddle. This has index -1. So there will be no 1, just q, 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 and q is -1. Okay, all the iterates have index -1. But you could also compose this with a half-turn rotation. Okay, this is the flip saddle. So this is index 1 because it looks like a rotation. But then the first iterate is the second iterate has index -1, and then again 1, and then -1. Okay. And you could imagine a multi-saddle with more hyperbolic sectors, and you compose by a rotation. And when you iterate, if it rotates, it has index 1. But at some points, it does not rotate. All the branches are fixed. It's hyperbolic, and it has negative index. Okay? So it's like this. And they say more about this. There is a relation between Q and the period, but that's enough for us. So that's the local dynamics. And now we come back to our minimal homomorphism of the two sphere minus north and south. So you see that there is some iterate such that north and south have non-positive index. But now Lefschetz tells you the sum of the index of the fixed point of f to the k should be 2. And there is no other fixed point because it was minimal. So there is a contradiction. Well, you can't have infinitely many, you can't put infinitely many hyperbolic sectors just by continuity because they are moving in opposite direction. Well, or another way to say it is that the index is finite and every hyperbolic sectors contribute to -1/2 or something like that. So you can't, the vector cannot turn too much. So that was a nice proof. Of course, this is a difficult theorem, but then there was a more conceptual proof by John Franks using the Conley index. And also what is nice is that Patrice went on studying the local dynamics of surface homomorphisms. And so yesterday, Anna told us about the local complex dynamics. So there are several cases, and there is a lot, we understand well the local complex dynamics. There are petas, or there are rotation, and so on. But what's amazing is that with almost no hypothesis, Patrice succeeded in saying many things on local dynamics of homeomorphisms. And so the general idea is that there are 3 phenomena, and you can understand in every situation there is one phenomena that happens. Either your fixed point is accumulated by periodic orbits, and usually you are happy because you are looking for infinitely many periodic orbits. Or the fixed point has arbitrary small compact connected sets, and then you are happy because you can use prime n to define rotation number and see how it varies with the local rotation set, and you have a tool to work, prime n. Or you are saddle-like, and then you can use Conley's theory and show that the indices gets negative at some point. So, and he used this study to find periodic orbits for Hamiltonian homomorphisms. It uses Conley index. So Patrice and Jean-Christophe, they study, so they take some Jordan curve and they iterate and they study the combinatorics of the iterates, and it's really complicated. And, but there is something called the Conley index, and when it's saddle-like, it's well defined, and you can use this. It's a homological index, and you can. So you get less because you don't get all the structure, the dynamical structures they get, but to prove the theorem that periodically you are non-positive index, that's easier. And so this Conley index was used later by Patrice with Roux and Paco in higher dimension, and they proved that there is no minimal orientation reversing homeomorphism on R3. And orientation reversing is there because that's when Conley index gives you some information. I think orientation preserving is unknown, no? So just every orbit is dense, like in the previous theorem. Okay. So I would like to say a word about generating functions. So Patrice introduced generating functions for surface dynamics in Perth. And so they are a very powerful tool to study diffeomorphisms. And it's a bit abstract. I don't really understand it, but I'm trying to give you the taste. So you take a torus diffeomorphism isotopic to the identity, okay? And so you write it as a composition of vertical and horizontal diffeomorphism. So this notion depends on the coordinate system. It's not conjugacy invariant. So that's, so, okay. You have coordinates on, you consider a lift of your diffeomorphism of the torus, F tilde, and on R2 you have coordinate system, and a vertical diffeomorphism is just something that it preserves every vertical line. So you just push vertically, okay? Horizontal is the same in the other direction. And so now you can, given any point, x, y, you can look at its image by F tilde, and you can define the following maps. You push vertically and then horizontally to get to the good point. So that's V1 and H1. And the remark is that if F tilde is C1 close to the identity, then V1 and H1 will be diffeomorphisms. That's an easy exercise. Okay. Essentially, the condition is that the image of the vertical foliation is still transverse to the vertical foliation. This is a C realized for C1 diffeomorphism, C1 close to the identity. So if F tilde is C1 close to the identity, you can write it as H1 composed with V1. And then if it's isotopic to the identity, the isotopy gives you a way of writing F tilde as a factor of small C1 small diffeo. And so each of these diffeo can be written like this, so you get this decomposition. Okay? So now from this decomposition, it's just a remark, I think. I mean, but so in Patrice's paper, it was not this decomposition actually in the first paper. This was decomposition by twist maps, but it's the same argument.
But that you use generating function when you compose. You took the map and you look at the composition of the map very close to identity. And when you're close to identity, you can take a system of coordinates. Usually it's f of x, y because x prime, y prime. You take x, y prime as a system of coordinates. But there is different ways to
so that way is Patrice's way, I think. And before, generating functions were used in symplectic dynamics, but for area preserving maps. That works for, you don't need area preserving.
You can write any diffeomorphism as a composition of a map. This interface is kind of thing.
Yeah, but it's
As the composition of a
but it's really
But here it's only differential geometry. I mean,
Yeah, sure.
okay.
And this group for any dimension, it will remain integer?
Yes, in linear and
So here you don't need any hypothesis on the diffeomorphism, okay? This number n is essentially the number of turns the differential dies under the isotopy. The more it turns, the more you need diffeomorphism you need. Okay, so what do we do with this decomposition? Well, you can look at the space. So we work in dimension 2n now, okay? And we look at the space of sequences of points in the plane, finite sequences of n points in the plane, and up to integer translations, okay? So this is homeomorphic to T2 times r to the 2n minus 2. And instead of sequences of points, this space E, so you have sequences of points, but you shouldn't think of them at discretized loop. So when you have such a sequence, you can consider the loop, which is the following. You go vertically and then horizontally from the first point to the second point, and then the same to the third point, and then the same to the fourth point, and say n equals 4, the same to the first point. So to this, any point in this space corresponds to this discretized loop, okay? And so from this decomposition of the dynamics, so the space does not depend on the dynamics. But from this decomposition, Patrice defined some vector field on this space, which has lots of nice properties. So the key property is that there is a bijection between the critical point of this vector field and the fixed point of f that leads to fixed point of f tilde. One way to imagine that is if you have a fixed point of f tilde, then you can put it in this factorization, and you get a finite sequence of points, and it goes back to start with z, and it goes back to z because you assume it's a fixed point of f tilde. Okay, so it gives you a loop like this. And xi, in general, can be seen as the defect. So if you take any loop that does not come from a fixed point, you see somehow the defect of the loop to come from a fixed point. So there is a formula, but
generating function in finite dimension space. These kind of things appear in the work of Koenig and Wendler, where they want to use but they use reduction to finite dimensional space. They work in infinite dimensional space, and they reduce to finite dimensional space by a process. I don't remember exactly the process. But Marc Chapon introduced the notion of broken geodesics. In broken geodesics, what we do the first time it was clear this way to get directly finite dimensional space. But broken geodesics were really used in the synthetic case. Here we don't need really the map to be synthetic.
No hypothesis. So if it's conservative, if it's preserved here, you get more. You get that the vector field will be the gradient of some function, and this is what you call generating function. And so Patrice proved in particular that you can find tori that are invariant. So in this big space, there are some two-dimensional tori that are invariant under xi, and when they project well one-to-one on T2. So since they are invariant, the vector field defines a foliation on the complement of the critical set, and this foliation projects on T2 into transverse foliation. So that was the first appearance of the equivariant foliated Brouwer theorem. So that's it. So in the first paper, it was only for fixed point free setting, but then Patrice generalized this for any C1 DFO of the torus, and also the PhD thesis of Arnaud Dehoff was about using these generating functions. And just to finish with this, more recently, much more recently, Patrice used this tool to prove Barnet-Bramham's theorem that every irrational pseudo-rotation of the disk may be approximated by periodic diffeomorphism. So Barnet-Bramham's proof was in infinite dimension using pseudo-holomorphic curve, and Patrice has this finite dimensional version that allows to do that. So it may be that you get this. Okay, now these are outdated because the equivariant foliated theorem is for Romeo on every surface, but you get more than the foliated. There are more structure to be used like in this theorem. So it's still, the generating function should still be useful. Okay, I will skip this one, I think. So we come to the equivariant foliated Brouwer theorem. Sorry? And linking was for you, but okay. So came to the theorem. So the theorem, as I said, it's a long work to get to the theorem. So first version using generating functions, and then the PhD thesis of Alain Sauzet was before that, and he used something called brick decomposition. He put this into form. There are lots of structure on the brick decomposition. He proved that to construct curves that are transverse to the dynamics, and now these curves appear at leaves of the foliation. So it's like now his results are application of the foliated theorem, but they are precursor of the theorem somehow. And there was the use by Fleischer and Guillou of triangulation to prove Brouwer's theorem. And then after the theorem, brick decomposition were used by Roux to improve Handel's fixed point theorem. Okay, and then I will put the statement of the theorem in the next slide, but then the theorem was improved by Olivier Jolland. Roughly, it allows to use the theorem in the case when there are infinitely many fixed points, and then Jingxi found torsion law isotopies, as she said, so she again improved the theorem in the area preserving case. And then, okay, there is the forcing theory with Fabio Tal, and Gabriel Lelouch is working on this, and I've decided to say not to say anything about forcing theory. Maybe I have to leave something for 2028, maybe. Okay, that's just a picture of brick decomposition. But so this is the equivariant foliated Brouwer theorem. Okay, so let me explain the statement once more. You saw it in Fabio's work and Jingxi. So you take any orientable surface sigma, and it's important to have in mind that usually it's not compact. And you take a homeomorphism so there are two important hypotheses. First, the homeomorphism is isotopic to the identity, and so there is an isotopy from the identity to F, and F has no contractible fixed point. So so when you have an isotopy on the surface, a fixed point of F is when you apply the isotopy and you look at its trajectory, it defines a loop, okay? And the loop can be contractible or not contractible. So the fixed point is called contractible, is when you follow the trajectory under the isotopy, it's a contractible curve in the surface, okay? So you assume there is no contractible fixed point. And then Patrice gives you an oriented foliation on the surface, which is homotopically transverse to the dynamics. So as Fabio said, you should not, so what does that mean? So you have your foliation on the surface, it's oriented, and transverse means that roughly speaking, that every trajectory is crossing the oriented curves from, well, we put the arrow in the opposite direction, so from right to left. Okay, always in the same direction. Except, okay, it's an isotopy and it's not, there is no reason it should go straight, so maybe it's making some dense step during the trajectory. And here it's not transverse, obviously. But you don't care because what you care is only the homotopy path up to endpoint. You have x, f of x. You are interested in studying f. You are not really interested in the isotopy, but it gives you some path up to homotopy. So this one, for example, is homotopically transverse because you could homotope the trajectory into a transverse path. Okay. So you can think the isotopy is really transverse. That it does not change anything about reasoning. Okay, so I would like to explain how you use this theorem. So you've seen it in action somehow already today. But of course, people who use this, they want to prove new theorems. So new theorems are hard to prove, so they work hard. And I would like to explain one of the most easy application of this theorem. And so there are two things you have to understand. Is first how you get into the situation when you can apply the theorem. How will you get this hypothesis? Because usually in dynamics you study Romeo is isotopic to the identity, so that's natural. But the second hypothesis, you have to work to get it. Okay, usually it's not satisfied. And the second thing you have to understand is why is it so interesting to get transverse foliation? So I will explain this in the context of Arnold conjecture. So this concerns Hamiltonian dynamics, as in Jan's talk, in Jan's thesis, and the PhD thesis of Benoit is also related to Hamiltonian dynamics. So what is the Arnold conjecture? So it concerns with Hamiltonian homeomorphisms on compact surface, and it says it has to have, okay, I have to explain what is a Hamiltonian homeomorphism, and I have to, so this, there is a complicated sentence at the end that's just a complicated way of saying if you are on the sphere, you will get at least 2 fixed points, and if you are on higher genus surfaces, you will get at least 3 fixed points. But really, you should think of 2 and 3 as being the minimal number of critical points of a smooth function on this manifold. Okay, so I will explain what is a Hamiltonian homeo, but just to motivate you, I've put a big parenthesis to put all the mathematicians who worked on this. So quick history on the Arnold conjecture. It was first proved for diffeomorphisms on the, so okay, on the sphere especially, it's not so difficult on the 2 sphere, but let's say on T to N, so it's about symplectic manifold, so only in even dimension, okay? So on the torus first by Conley-Zender for diffeomorphisms, and then it was generalized on symplectic manifolds. So, okay, there may be still some hypotheses here. Fleur also?
The first
at that date. Okay, by Fleur also probably, no? Or
I think the first paper was on surfaces. At the
okay.
same moment of Sigora,
Okay.
and after Fleur developed its theory for higher
okay. Okay, so
maybe I make a mistake, but I think
okay, so I'm missing.
maybe I make a mistake.
Okay, so C curve extends to surfaces, and at least one important point is that the Flood developed his whole homology theory, which is now an industry which make busy hundreds of mathematicians. At the beginning, it was that was the big motivation. And okay, so maybe some other guys on symplectic manifolds, I don't know. And then for homeomorphisms, well, on T2, John Franks find one fixed point, and then Flusher found the second fixed point, and then Patrice found the third fixed point. And then on higher genus surfaces, Shigenori proved that there is at least 3 fixed points using Handel's fixed point theorem. So, okay, let me explain what is a Hamiltonian homeomorphism. So Jan already gave some definition. So of course, the name Hamiltonian comes from Hamiltonian smooth dynamics, and one way to define this is, say, you take a homeo, which is the C0 limit of a sequence of Hamiltonian diffeomorphisms. But that's not so enlightening when you are making topological dynamics, so there are some topological way to define this. So F is Hamiltonian if, so first, easy thing, it should be isotopic to the identity. Then it's area preserving. And then there is a third condition that, okay, each time you consider a closed curve on the surface, like this, you can look at, so you have an isotopy I from the identity to F, and you can look at the trajectory of points through this identity, and some points are crossing this curve, okay? And you can define the mass, the measure of points that are crossing the curve during the isotopy. One way to, so it's really the area between the curve and its image, but you need the isotopy to define this. So one way to define this is say, okay, each time I have a point x, I look at the trajectory ax, and I take the algebraic intersection number with this curve. Okay, this is well defined for almost every point, and I take the average number. The curve gamma is given. This is the flux through gamma during the isotopy I. Okay, this is the definition. And you say it's Hamiltonian, this is 0 for every curve. This is the hypothesis. So another way of saying this is that the mean rotation number is 0. This is somehow just Birkhoff's theorem. If okay, you could take the asymptotic crossing number when you iterate, and by Birkhoff, this will have a limit for almost every point, and the integral of the limit will be the same thing as this. So the mean rotation number is the same thing as this. Okay? And you can note that being area preserving is the same, but for contractible curves. Okay? If you preserve the area and you have a disk, its image has the same area. And saying this is saying that when you apply the isotopy, the quantity of area that goes through the boundary is 0. Okay? The area that goes outside is equal to the area that goes inside. So this is a natural extension to non-contractible curved. So, okay. And one good thing is that there are lots of examples of this, because that comes from Hamiltonian formalism. So you have a surface. Each time you have a smooth function from your surface to R. So here the function is just the height, the z coordinate. Well, there is Hamiltonian formalisms gives you a way to define some dynamics that takes place on the level set of the function. Okay, something like this. Essentially, what it gives you is say there is a unique way of pushing points along the level set of the function so that the area is preserved. So this gives you, and this gives you an area-preserving Romeo, but also a Hamiltonian Romeo. So there are lots of examples. So it's a rich word. And of course, if you take an example like that, the critical point of H will be fixed point of your Hamiltonian diffeo. And this gives you an example where the statement is obviously true. Okay, so how do you prove this theorem from the equivariant foliated Brewer theorem? So that's the proof is almost immediate, and that's one of my favorite pieces of mathematics. So, okay, you have a Hamiltonian homeomorphism on a surface S, and you want to prove there are at least, say it's the torus, and you want to prove that there are at least 3 fixed points. So the first thing you remember to be able to apply Patrice theorem, you should be in this situation. So something isotopic to the identity, but no contractible fixed point. So this is why the notation is not the same. Because this won't happen on your surface S. You have to remove some points to get here. So this is what you do. So you are on a surface. So F is isotopic to the identity, but you can't apply the foliated theorem because maybe there are some fixed point of F that are contractible under the isotopy. Okay? So if you have a contractible fixed point, one key lemma, easy lemma, but important, is that you can modify the isotopy so that the point is fixed during the whole isotopy. That's easy. It's just a vibration lemma. So then you can modify the isotopy and remove X from S. Okay, so now there is one hole in the surface, and maybe there are still other contractible fixed point, and again you modify the isotopy so that they become fixed. So not at some point that maybe were contractible at the beginning, now you have removed point, so maybe they won't be contractible anymore. So this one does not bother you anymore because you have removed this from the surface, so it's not contractible anymore. Okay? So if you have a finite number of fixed points, if F has a finite number of fixed points, remember, we are trying to prove there are at least 3 fixed points. So if there are infinitely many, you are done. So you can assume there are finitely many fixed points. So playing this game, at some point, there won't be any contractible fixed point anymore. So you will be in the hypothesis of Patrice theorem, and there will be a transverse foliation. Okay? If there are infinitely many fixed points, you need some other theorem to say you can remove some good part and have a good isotopy. So a good isotopy is an isotopy so that every fixed point of F, either it is fixed by the isotopy, and then you remove it from the surface, and you define the complement to be a surface, an open surface sigma, or its trajectory is not contractible in this sigma. So then you can apply Patrice theorem. There is an oriented foliation on sigma, which is positively transverse to E. And now, remember, you had a Hamiltonian Romeo. So if knowing that F is Hamiltonian, Patrice proved that the foliation is gradient-like, which really means it looks like the flow of a gradient vector field. For example, one thing that could happen, which is not gradient-like, is having a closed leaf. The foliation could a priori have a closed leaf. But if you are transverse to a foliation that has a closed leaf, this means that all the trajectories that are going through these leaves, they are going in the same direction. So the flux through this closed leaf is positive. But you are Hamiltonian. You assume the flux is 0 through any closed curve. So this does not happen. There is no closed curve. And likewise, you can prove many things don't happen. There is no cycles, for example. So every trajectory, every leaf of your foliation F goes from one singularity. So the singularity is just, by definition, the set of fixed points of the isotopy that you have removed from the surface. Every leaf must go from one singularity to another singularity. Okay? And the singularities are either sinks or sources or saddles. There are only 3 types. Okay, and now it's done, no? Because the foliation F has at least one source and one sink. Because if you have a saddle, well, you have the stable manifold of the saddle, it comes from somewhere. So you go up and you find another fixed point of the isotopy, singularity of the foliation. If it's still a saddle, you can still go up. And you go up, and at some point, there are finitely many fixed points. So at some point, you get a source. And likewise, there is a sink. And if there is only a source and a sink, you have only 2 singularities of index 1, so you are on the sphere. And if you are not on the sphere, you must have a saddle, at least one saddle. So you get 3 singularities for the foliation, but the singularities was fixed point of the isotopy. The fixed point of the isotopy are clearly fixed point of F. So you have find 3 fixed point of F at least. Okay, so this is a very clear and conceptual proof of Arnold conjecture. Okay, I still have 5 minutes, so I can show you. This statement. So maybe just the last one. So this theorem was also proved by Patrice using his foliation and playing with a maximal unlinked set. So it was an answer to a question of John Franks in '88, and 20 years later, Patrice proved this. So you take a Homer of the plane and isotopy to the identity, and you assume there is a periodic orbit. So Brewer theory tells you there is some fixed point, because fixed point free homomorphism, orbit goes to infinity, there is no recurrence, no periodic orbit. But the question was to know that if there is some fixed point which is linked with the periodic orbit. So there are several ways to define what this means. One way is to say if you have a fixed point, when you remove the fixed point, you have an open annulus, and the periodic point has some rotation number in this annulus. So you say that the periodic point and the fixed point are linked if this rotation number is not 0 modulo 1. Okay. Another way to say this is that you could, okay, F is isotopic to the identity. So there is an isotopy, and so maybe, okay, I should do this picture. So, because really it's braids that are under this. So you could represent the isotopy using a third dimension, okay? You put times here, because this is t equals 1, t equals 0, and when you have a point here, you can follow its trajectory by the isotopy on this picture. At level t, you draw ft of x. So if your point is fixed, you get some strand like this, which goes from x to x. And if you have a periodic orbit somewhere, say period 3, okay, I won't be able to. So you have y, and f3 of y is y. So when you put the trajectory of those 3 points, you get a braid, because the 3 points, you can picture them here also. And so, so this one is going here. It should go, okay, it should not be crossing, it should be before. And then y is going there. then f of y is going there. And since those 4 points are the same are here, this is a braid. And this braid should be the rotation, the braid of a rotation. This is another way to say it is linked. Okay, so I will stop now. So I've put all the Patrice students and collaborators here. So okay, lots of them are here. So I would like, thank you. So I would like to thank you for being there and for being so cheerful and so nice. I would like to thank the organizers for all the work. It's hard work and everything is perfect. And of course, I would like to thank Patrice for all his mathematics. That was said before. I also personally have a great depth. Lots of my mathematical work comes from ideas of Patrice, either directly or indirectly in his paper. And okay, and also I think everybody is aware that he's a very nice person. It's very pleasant to talk to him. And okay, but I would like to say that also he's in my lab, and I at a higher level, in every professional occasion, he's really always acting very nicely and in an appropriate way. And that's very important because, okay, maybe especially for young people, you should be aware that if this community is surface dynamics, it's very healthy and very sound. I think it is. And it's not something automatic or random. It's because people are behaving nicely. And of course, in that respect, the big guys, Patrice and Shigenori and John Franks also, they are very important. They are models. And okay, so thank you very much for this.